Now we will try to understand Kepler's three laws of planetary motion. So first law is telling the orbit of any smaller body about a larger body is always an ellipse, with the center of mass of the larger body as one of the two foci. Second law is the orbit of the smaller body sweeps out equal areas in equal time. And the third law is the square of the period of revolution of the smaller body about the larger body equals a constant multiplied by the third power of the semi-major axis of the orbital ellipse, that is t square is equal to 4 pi square a cube divided by mu, where t is the orbital period, a is the semi-major axis of the orbital ellipse, and mu is the Kepler's constant. Now if we consider this ellipse as a orbit of the satellite, then the Earth must be placed at one of the foci of this particular ellipse. Okay, now consider this particular law, that is the second law. It is saying that the smaller body sweeps out equal areas in equal time, or in other words, the aerial velocity is constant, right? What happens? The distance of the satellite from the larger body, that is Earth, governs the velocity of the satellite, right? Obviously, near this location, the velocity will be higher, and near this location, velocity will be smaller. Okay, suppose from time t1 to t2, right, the satellite has moved from this location to that location, covering area of this much. So this is the area covered by the satellite between t1 and t2. Okay, now consider the same satellite is revolving around the Earth, and it is covering this much amount of area within the time of t3 and t4. Okay, so area for this case is 812, and area swept out by the satellite is 834. According to Kepler's second law, this A12 and A34 will be same if T2 minus T1 or T2 difference T2 T1, T2 difference T1 and T3 difference T4, they are same. That means within the same time gap, the satellite sweeps equal amount of area, which is nothing but the Kepler's second law. Okay, simplify the equation of the orbit, we can set theta 0 equal to 0. That means we orient the uh, orbit, or in other words, we have chosen x0 and y0 in such a way that theta 0 becomes 0. Okay, so equation becomes simpler, and the length a and b of the semi-major and semi-minor axis, that can be determined from this equation. It is a equal to p by 1 minus e square and b equal to a into 1 minus e square whole to the power half. The point in the orbit where the satellite is closest to the Earth, that is called the perigee, and The point where the satellite is farthest from the Earth is called the apogee. Perigee and apogee are actually always exactly uh, in the opposite side of the orbit. Now, differential area swept out by the vector r0 from the origin of the satellite is time in time dt, that we can write in this way. So if we observe the orbit, we can see that this is the position of the perigee, this is the position of the apogee, and this is the position of the Earth. Actually, this is the focus of the ellipse, and this is the orbit of the satellite. So this is the distance, this distance, and this is the a into 1 minus 1 plus e is this distance from the center to the focus is a into e. E is the eccentricity, and h is the magnitude of the orbital angular momentum. And we have already seen that the relationship between the time period and the radius of the circular orbit, but we can easily prove the same thing for the elliptical orbit as well. So t square equal to 4 pi square a cube divided by mu. An important point to remember is that the period of revolution, that is the capital T, is referred to inertial space, namely the galactic background. The orbital period is the time of orbiting body takes to return to the same reference point in space with respect to the galactic background. Now, nearly always the primary body will also be rotating, and so the period of revolution of the satellite may be different from that perceived by an observer who is standing still on the surface of the primary body. This is most obvious with the geostationary Earth orbit satellite. The orbital period of geosatellite is exactly equal to the period of rotation of the Earth, that is 23 hours 56 minutes 4.1 second. But to an observer on the ground, the satellite appears to have an infinite orbital period. It always stays in the same place in the sky. So that is the beauty of the geostationary satellites. Though it is revolving around Earth, but the period of revolution of that particular satellite and Earth is the same. So when we try to see the satellite in sky, at every moment we will see that particular satellite in the same place, as if the satellite stands still in the sky without changing its position. So it is appearing to us, it will appear to us that it will stay in the sky without changing its position. So that is what we call the geostationary satellite.